Hello YouTubers, welcome to this next session about how to use a multimeter for beginners, and in this session we're going to basically cover off how to measure current. The few other things we are going to do, we're going to go through the answer to the question that I posed on the first session. We'll then go through just to explain some concepts with that answer, because it does help with an understanding of how electricity works, in particularly AC and DC. I'll then pose a new question for the next video that we'll review, and then we'll get stuck into the actual how to measure current with a multimeter. So for those of you who may have started this video looking for a quick 3 or 5 minutes solution on how to measure current, you're not going to find it here. This video will probably run into 20-30 minutes. There are loads of videos on YouTube which kind of give a quick, simple parrot answer to that. This video is for those of you who want a really good understanding of some basic concepts on electricity and how to do those, make those measurements with a multimeter. So let's get stuck into it. I'll quickly go through some of the answers. Now, first of all, thanks very much to those of you who did respond to the question. I'll just repeat the question again. Basically, I said, which was more dangerous, AC power or DC power? And I just left it like that with no other further detail. And a number of you came back, and some of the answers were certainly fairly off the mark and not correct, but that doesn't matter. Just attempting to answer a question and getting it wrong is great. There's nothing wrong with putting something out there that you may think is right if you can learn from it. If I was worried about making mistakes and saying the wrong thing, I wouldn't even turn that camera on each time I wanted to do a video, because I'm constantly making mistakes. You don't be scared. You learn from your mistakes, jump in, answer the question, don't worry. There were some good answers, a lot relating to, in particular, it obviously depends on the amount of voltage and the amount of current involved, which is very true. A combination of those two is ultimately what can be very dangerous and can kill you, both on an AC side and a DC side. But the answer I was kind of looking for, and I'll explain more about it, and if it sparks debate, that's fine. But basically the answer that Todd Harrison gave, and I'm going to read out his answer. It covers most of what I was hoping to hear, but I will then go further, and it kind of brings out a concept that we need to understand between AC and DC. And it says, I'm going to say DC is more dangerous to work with because once you touch something with DC, your muscles will contract and stay contracted, making it impossible for you or others to remove you from the power. With AC, your muscles would be pulsing on and off, giving your reflexes a chance to pull away or someone to knock you off the power before even more permanent damage is inflicted. And that is very true. I can attest to the fact, and this is something I learned when I was studying my electronics, the dangers of DC versus AC. That's what DC does. DC is constantly on. It's not like AC, which is going through a cycle of being on and off and building up and coming on and off. It's permanently on at that voltage. And so in essence, if you get a shock from DC, your muscles contract. If it's let's say a piece of wire or a contact that you're holding on to, your muscles contract and potentially keep you there, delivering a lethal dose of electrocution. Whereas AC tends to actually throw you back. And I can attest to that, because about a week and a half, 2 weeks ago, I managed to give myself a shock on 220, and it threw me back. And I sat for a while with a little bit of a shake-up, but that's what AC does to you. So that was the answer I was kind of looking for. And DC is dangerous in terms of far more aspects. DC, when it comes to electrical components, high DC at high current becomes very challenging, and in fact the components, particularly even switches and breakers, become very complicated because in essence, you weld with DC. So the amount of power you're getting when you've got direct current, you can weld metals together. With a couple of car batteries and some contact, you can actually weld things together. Switches after 10 amps, it's amazing. DC switches below 10 amps are relatively cheap to buy. As soon as you go above 10 amps, 15 amps, you start approaching 20 amps. The contact and breakers inside a switch, when they slap together, you potentially get arcing, and they can actually then weld themselves together. But anyway, I'm going to put a diagram together, and we'll go through that, and hopefully that'll give you a better understanding. Okay, so let's get stuck into that explanation of AC versus DC. But before we do that, again, I just want to thank Comtest again for the loan of this Fluke multimeter for this tutorial. They kindly do loan me this equipment. If you follow any of my other videos, you'll realize they actually loan me some quite interesting equipment, particularly for the solar side as well, which I certainly wouldn't be able to get my hands on if they weren't on board with this. So thanks very much to them. Right, so let's get in a little closer to this diagram. We don't want to get too advanced or too technical, but let's try and get a basic understanding from my little scribble diagrams here. Okay, so we're going to take, so sorry to the Americans, we're going to kind of use a European / South Africa standard for this one, of an average around 230 volts. So if you can imagine, your x-axis over here is time, and the y-axis is the voltage. Now what happens with AC, the voltage goes up to a peak, then comes down to 0, then goes negative for a while, and then comes up to 0, and it repeats the cycle again. And depending on where you are in the world, it either happens at 50 Hertz or 60 Hertz, which is either 50 times a second or at 60 times a second. Now, this, just to get an understanding, for an average or a comparison to say a comparative equivalent to a DC voltage, but it's a naughty analogy to make, but some people do. But to get the average voltage of what you're getting coming out of your mains outlet or what have you, of 230, the voltage actually goes up to a peak of 325 volts, and then comes back down, and then goes down to a negative 325 volts. So you've actually got a peak-to-peak voltage of 650 volts. Now what happens, what we're doing, what the useful voltage for powering your appliances or whatever at home is the average under these two bits over here, under these two cycles. And that, you'll hear about the term on a multimeter called an RMS multimeter. That means root mean square. And that's a calculation to understand the average of this area under here, and that is 230. Okay, so as you can see from that, so basically in AC voltage, it's kind of like, and one analogy is like thinking of an old steam locomotive with the pistons going back and forth. It literally is shuttling back and forth in essence in that piece of wire, doing its work by doing that, as opposed to DC, which is just plowing straight forward the whole time. So if we go to the DC side, let's say we had an equivalent DC voltage of 230 volts DC, it would look like this. And if you had this on an oscilloscope, that's what it would look like. Okay, on an oscilloscope you get a nice wave like that representing your AC over time, and on DC it would just be a flat straight line like that at your 230 mark. That is just constantly on. It's not, you can tell that with an AC voltage, there's a lot of time when it's way below that kind of even the 230. It peaks at 325, but then it's coming right back down again, and then it hits 0. The negative side, although it's negative, it's still going to hurt you, but the negative side, obviously, it's building, it hits its peak, and then it comes back on. And that's that buzz. If you've ever touched AC, it gives you that buzz. but it's going on and coming off. So it actually gives you a chance to release, or in fact kick you off if you get a shock. Whereas DC, you're just getting the full-on 230 all the time, and it'll grab you and clench you on. So that was kind of basically the answer I was trying to get to. And more importantly, the reason I wanted to kind of demonstrate this answer, and it doesn't mean the other answers were wrong. In part, they were right in what they were saying in terms of the makeup between current and voltage and what have you. But I just want to stress how dangerous DC in particular can be. Generally speaking, we think of DC with little batteries and 12-volt car batteries, and of course on a 12-volt car battery you can put your fingers on the two terminals. It's not going to shock you. Why isn't it going to shock you? Perhaps that should be another question, but it's not going to shock you because it just doesn't have, there's enough current in a car battery to do damage, but the voltage is low, okay? But DC, like in particular, one application I can tell you where you can potentially get high DCs in solar panels linked together in series. You can get 300, 400, 500, 600 volts plus, and there things become very dangerous. If you had the wires between two solar panels which were linked in series built with that high DC voltage together, and you had a continuous circuit, i.e. you didn't break it somewhere and you had current running, and you pulled that apart at 600 volts, you would be in potentially for a lot of trouble, because it would arc. It's like lightning. It would arc between those two contacts. So that's where you have to be very careful with high voltage DC. I say electronics and what have you, different stories. The current levels and the voltage levels are a lot lower. So I wanted to pose another question for the next video, and that is basically when electricity was first started being used mainstream, and there were power stations generating electricity and transmitting it to houses for lighting and what have you. They initially started off with actually transmitting DC, believe it or not. And they later switched over to AC. And I'm keen to understand if someone can give an explanation as to why. Okay, so that is the next quiz question for next week. As I said, take a stab at it. If you're wrong, it doesn't matter. But post an answer and we'll discuss the answer in the next video. Okay, let's jump into what we're here for, and that's to understand how to measure current. Okay, so before I want to go back to the diagram and give a little analogy again of understanding what current is. But I thought just a quick look back at this Fluke 177. When we do current readings, we're going to be popping these banana plugs into different connectors now. The black still will remain in the common, as it does for all measurements. But this time the red will go either between the 10 amp or your main ampage, which is generally the case on most multimeters, the 10 amp connector, or your milliamp connector. And that can vary from multimeter to multimeter. It can be as low as 200 milliamps. It could be 500, 600 milliamps. As I showed you earlier, some multimeters just have, and I'll demonstrate it here on this Fluke, some only have 3 connection points, and this is more for electricians. They just have a connecting point to measure amps, higher amp values. You can measure milliamps, but not down to the resolution that you can on, let's say, a multimeter like this. The wisest thing always is to always start off in the higher setting down here. I would advise that if you own an existing multimeter which isn't fused, I would recommend getting one that's fused. I'd also recommend getting one that definitely has separate plug connectors for your current, and it's not shared with the voltage, and we'll cover that why a little just now. But having fused points for your milliamps and your amps is important. As I said, always start on the higher one. When you realize your current level is safe, you can then flick down to the lower one. But let's get in and have a look and an understanding about what current is. So we're going to go back to this diagram I did in the first video. As I said, just like a garden hose has got water in it, just like a piece of wire has electricity flowing in it, there's two components which are fairly similar. You have pressure pushing the water out, and that we regard as voltage. And I said it's like tapping in a little hole in the pipe and putting a pressure gauge in there. You can, relatively speaking, with a few caveats, actually fairly safely take high voltage readings, because you're just tapping in through a little hole, you're just taking a reading off your piece of wire or what have you and getting a pressure reading, the voltage. However, when it comes to current, it's a different story. For current, just like let's say in a pipe, this gauge over here cannot tell you the volume or amount of water flowing in this pipe. And that, remember, that is current in essence. That's your other aspect. Current is the same as, it's the volume, it's the amount of electricity, or relating to this diagram, it's the amount of water. So to be able to understand how much is in there, you have to put, let's say we had a little paddle inside this flow of water. You have to excuse my diagram, just pretend it's a nice little paddle that's in this flow of water, which will measure the volume flowing past it. Okay? And therein lies the little challenge that we have to be aware of. You have to place your measuring device inside the flow. There is a caveat to that, and I'm going to come back to that. But for the most part, for the basic side of measuring current with a multimeter, you need to place your multimeter in the flow of electricity. So, when we come back to our multimeter, when you take your probes, this time, as opposed to, say, being on the outside of your circuit in essence and just taking a pressure reading, these probes now become part of the circuit. The electricity that you're trying to measure is going to flow through your one probe and out of the other. Through the probe, through your multimeter, and out the other. And that's where measuring current can be a challenge, because your multimeter has to be able to handle that flow of current. And current can potentially generate heat, it can melt things if it's too high, and that's why by default most multimeters are only going to allow you to measure up to 10 amps. Some will allow you to measure to 15 or even 20 amps, but only for a very short period of time. There's not many multimeters that allow you to measure higher than that. The caveat to that is you can measure current in a safer way, and that is something you can do it with a current tap. So as I said, you can do it with a current tap, or you can do it with a special multimeter that has a clamp. And this clamp basically can read current, an induced field, the magnetic field around a conductor, to measure safely without breaking a circuit high currents. But we're not, that is something that we will cover in a more advanced series. I just want to put it out there that there are other ways. You can even use a current shunt, and that is something else we'll cover off when we move to the kind of advanced series of videos on this topic. Okay, so let's get stuck in. We're going to get something to measure, and I'll explain again how we're connecting everything up and how the current is actually flowing through your multimeter. Okay, so I've got all the components that we're going to use for this little test. I thought I'd just quickly show you what we've got. We've got in essence a car headlamp here. We've got the multimeter, we've got the probes, and we've got some attachable crocodile clips. Now, someone made a very good fair comment in the previous video and was stating that, if you remember, I used those little crocodile clips to connect to that LED when I was measuring the voltage across it and what have you. And they said that perhaps that wasn't, there could be some safety issues with that. Now, they were dead right. In that application, though not, the measuring voltage, you can get away with using some crocodile clips and thinner wire, but at the end of the day, it's good practice to always try and be safe. And the safer thing to do to have crocodile clips on your probes is to get ones that attach directly to your probe, like the ones I have here, because they can handle more current. But I'll demonstrate that now. Then the other thing I wanted to show you, so I've got my variable power supply up here, which is what we're going to use to power the headlight. I've already got it set at just over 13 volts, and the maximum I've got it set to, I can vary the current that it's going to put out. I've got it set to 3 amps, and I can tell you now this car lamp would actually draw far more than 3 amps if my power supply could put that out. But it's enough to get it started, so we'll hook it all up and see how that works. Okay, so first of all, the first thing we need to check, we've got our multimeter. As I said, hopefully you've got a multimeter which has separate inputs for measuring current. It's far safer that way. Potentially if you have shared inputs on voltage, on your voltage input, then if you make the wrong selection while you've got things cabled up, you can cause a short and blow things. So for now, as we can see, we've got our black in the common. We're starting off with our red connector in the 10 amp connection, okay, not in the milliamp, because potentially we don't know what current we're going to measure. I know ahead of time we know what we're going to probably see, but potentially if you don't know, always start in the bigger one, okay. Then what we're going to do, I'm going to clip on these crocodile clips onto the probes, make sure they're nice and firmly connected, okay. Then what we're going to do, I'm going to connect, as rule of thumb, and what I do is basically your live feed coming from your source voltage goes to your live or your positive on your multimeter, okay. Then in essence, and this is where it gets a little bit confusing, your black probe on your multimeter isn't acting as a negative this time. You're feeding, this is one line of the circuit, the positive line of the circuit, and I'm going to show you in a diagram, but this is a positive line of the circuit which comes around through your multimeter. It's still positive, it comes out here, so this needs to go to the positive connection of the load that you're trying to feed electricity to, or your DC voltage to. So that's clipped on there like that, and then I can directly take the negative, in essence is this side, this is the negative side of the power supply. It gets connected like that, and what we want to make sure is that the wires are all apart and we're not going to get a short. So I've got them laid out like this. Let's make sure they're not going to touch. They look, I'll even pull these wires apart to make sure not, so that looks safe. So what I'm going to do next is we need to select the correct setting on the multimeter. So we move around the dial, we go past all the voltage selections, we've got ohms, we've got continuity, then we've got milliamps. Now remember I said we're not measuring milliamps, we've gone to the bigger setting, amps. We put it onto amps, and on this Fluke, so that, as I said, the thing you do need to note in particular on this Fluke 177, it defaults to AC. Okay, we're not measuring AC, you'll get an incorrect reading. So we need to select this kind of second function button over here, the orange one, and that then takes us to DC, as you'll note on the display there. Okay, so we're all set up. Let's pull this up so that you can see what happens when I switch on the power supply. I'm switching it on now. I don't know if you can hear that. There's a nice big hum that comes from that because it's drawing so much current. And you can see the light has come on. And what are we reading? 3.030 amps. So that's a fair amount of current. It's not a huge amount, but it's still a fair amount. Had I gone and used this 400 milliamp connection first, I'd have blown the fuse. On this multimeter, it wouldn't have caused any damage, but it certainly would have been inconvenient. You're potentially not going to have spare ceramic fast blow fuses lying around. You're well equipped if you do, so then you're going to have to go run off to the hardware store and go get the correct fuse. Don't be tempted if you do that by accident, by trying to short out the fuse or put in an incorrect fuse. You'll potentially damage your valuable multimeter. So there we go. Let's get a diagram so we can just see what we've done here. Okay, so I've got this simple diagram here. Now what I'm going to do is I'm going to first block this out because I want to demonstrate in essence what we did the other day when we did the voltage measurement. We had a battery, and I said, although it's commonly, I just had a single 1.2 volt cell, commonly called as a battery, but it is in fact a cell because it is just one cell. Many cells together form a battery. We had the power supply feeding a load. In this case it's the light, and here we had our multimeter, digital multimeter. We had the common, which in that case in essence it acts as your negative because we're working with DC, and we had our positive on either side to measure the voltage. Now what happens, you get your, whether it's a power supply or a battery feeding your load, all of your current and electricity is basically flowing through your load and around like that. That's your continuous circuit flowing around like that. Your digital multimeter, when you got it set to volts, has a very high resistance, so it doesn't allow much current to flow through itself. It is minuscule, and that is how, remember, it's like that little pressure gauge in a pipe. It's just tapping in to measure the pressure. Okay, so it's not in essence really forming part of the circuit at all. Now what we're doing today and how we had things connected up is a different story altogether. We've got the power supply, and as I said, we had the positive connected to that positive red probe of the multimeter, and then we had the black, sometimes referred to as negative if we're measuring DC, but in essence it's the common. But that common in essence is feeding the positive feed out to our load, to our light, and it goes then through the light and back to the power supply. But as you can see, your digital multimeter forms part of that circuit. All that current which you're trying to measure, which is flowing through your light source, has to flow through your multimeter. Your multimeter here in essence has a very low resistance to that flow of electricity. Now we're going to learn about resistance and continuity probably in the next video, but that's the important thing to note when measuring current. If you don't do something more advanced like having a current tap or current clamp or a shunt, the common way for measuring current is like we have it set up now, and you have all your current going through your multimeter. So that's the circuit. Okay, and as you noted, we're measuring about 3 amps. So now we're going to just measure something a little smaller to show how we can measure a smaller current or ampage. Before we get to measuring that smaller current, there's something I actually wanted to note which I picked up while doing this demonstration. I'm going to switch on the power supply again. There we go, the light comes on. This wire, which I'm using from my variable power supply, is actually quite cheap wire that I picked up at my electronics shop. It doesn't have any rating on it, and neither on the packaging that it came in did it have a rating. I mainly use this to power small DC electronics. But I can tell you right now, even with just 3 amps flowing through it, I can feel this wire starting to heat up in my hand. It's got nothing to do with this light source or the little bit of heat that's coming off here. This wire is starting to heat up as we speak. And that is something very critical you have to note about current, is that thin wire can potentially handle quite a high voltage, but when it comes to current, it's a very different story altogether. That high volume, that high flow of electricity wants bigger wire, and that's something we will address again in later videos. I say this, if you feel wire heating up like I wish, the temperature is literally getting very warm, that is potentially going to cause a fire if it is left in that kind of state. It also means you have losses. You don't have, you lose a lot of your energy and power that you're trying to supply a source load with. Okay, let's move on. Okay, so now we're going to do a measurement of the current which is used by the current, or the ampage, which is used by this little red LED. So I'm going to connect it up, and again remember, we've still got the multimeter connected in exactly the same way. Even though we know this is not going to use much, we're going to err on the side of safety. We've got it connected to the 10 amp connector here. We've got the power supply coming into the red lead, the positive, which feeds through. So remember, this is acting as the positive, and then this negative back to the power supply. And on the LED, you probably won't see it on the camera, but if you're going to try this for yourself, the LED, there are little metal pieces which go, you can see the bigger one is actually the negative and the smaller one is the positive. So that's the way I'm connecting it up over here. I'm going to set that down there. I'm going to set my power supply below 1 volt because it won't take much to light up this LED. We've got our multimeter on ready, and remember, if you on the 177, if you happen to change any of the settings, it's going to default back to AC. So remember to use the secondary function key here to go to DC, which is noted, as you can see here on the multimeter, it's got in orange the DC symbol above the AC symbol, which is the default. Okay, so I'm switching on the power supply. Let's have a look and see if that, at what level that LED is going to come on. I don't know if you can see that. There we go. I've got it up at about 2 volts. And you can see it's at 0.008 amps. So that's not a very fine reading, but we now know that it's below the 10 amps, so we can safely state, right, well, this isn't going to give us enough resolution. And when I use the term resolution, if you want to understand the terms accuracy and resolution, you can, I've got a good video which I'll add a link to on this one now, so that you can go and view, which explains all about resolution and accuracy. But the resolution here is perhaps not enough for us to understand exactly what this is using. So now we can go and change things over. So I'm going to switch off the power supply. I'm going to simply change the red connection point to the 400 milliamp. Okay. As we saw, 400 milliamp, it wasn't near 400 milliamp on the multimeter. We can now go to the milliamp setting on this Fluke 177. So I've switched it over. Again, note it defaults to AC. We push the orange button to give us a secondary function, which, as you can see on here, hopefully the light's not obscuring it too much. I'll tell you what, I'm going to come in for a quick view just so you can see that. As you can see, the secondary functions on the current readings here are the DC ones. The straight line with the dashes underneath, and that's reached by obviously pushing that button over there. And as you can see, we've now got DC. Okay, so let's come back up and have a look. I'm now going to switch on the power supply again. Watch the LED. LED comes on. Wow, so now we get a reading that's a little more easy to read, a little more accurate, and we've got better resolution, because now you can see over here it's showing small m, big A, milliamps. Okay, So milliamps, 10 to the minus 3, 6.1618. So not many milliamps flowing in here, but there you go. We're forming part of that circuit, and that's how we can read current, or the volume of electricity being used by this LED. And that's quite an important fact, because later down the line, when we come to do some more advanced measurements like power consumption, you do need to know voltage, but the more important fact besides voltage is the current which is being used, the amount of electricity, because that can help you understand what size battery you need, what size solar panel you need, or how much power your house is using, or a particular appliance. So that's when things really do get interesting, and again we'll cover that off when I start the more advanced series on doing measurements with a multimeter. So there you go. What I'll do just for fun, I'm going to drop the voltage a little bit so we can see how the reading goes down on the multimeter. This is obviously set to auto range at the moment, so it'll pick up the right range. On the Fluke 177, you've got this range button where you can go and manually select a range. So now it's only showing us 0.1 of a milliamp. You can go and select different ranges for your own preference, and if you hold it down for about 2 seconds, it goes back to auto, which is the far easier mode to use it in. There are times when you want to go to a manual range, when you want to see a particular resolution or reading, then that's where it can be very useful. But again, here we go. I've just put up the voltage, and it's now using 14.36 milliamp. And shall we have some fun and games? Shall I blow this again? I'm going to increase the amount of current that my power supply will give. We're at 2.51 volts at the moment, and as we increase the pressure, it's allowing the LED to use more and more current. So what are we up to? 50, getting towards 60. Would be nice to see what voltage that's going to go at too. So I tell you what, I'm quickly going to stop here. I'm going to get another Fluke multimeter and we'll measure the voltage at the same time, just for a bit of fun. Okay, so what have I done here for a little bit of fun with this demonstration? As per the diagram, I've actually got things connected up as they are here in this diagram that I showed you earlier. We've got our Fluke 177 connected up so that it's in the path of the circuit. It's part of the circuit to measure current, the volume of electricity flowing through our light, which is an LED this time. And then this digital multimeter over here is a Fluke 115, which is connected up so that it can measure the voltage. Okay, so in this case you'll see I am using these nasty little crocodile clips and these thin wires, but remember, for voltage you can get away with doing that. It's not best practice, but you can do that because you haven't got a lot of current flowing through these. So here they are, positive, negative. Positive lead is on the positive side of the LED over here. Negative is over there, positive is over here. On this multimeter, I flick through to the voltage, DC voltage, black in the common, red is on the volt side, and I'm going to switch on the power source again, so keep an eye on the LED. Let's see when the LED does light up, you'll see the voltage. There we go. I can see, you can just see it come on there. And what are we at? About 2.2 volts. So now you're seeing basically exactly what my variable power supply is putting out. I'm going to step the voltage up until we blow the LED. Let's see what happens. Let's note the milliamp readings. Ooh, we're getting up to 2.7. How much current and voltage can it take? 60 odd. I wonder, can I smell something? 3.2, let's step it up a bit quickly. 80 odd milliamps. Almost a hand. I can see it changing color at 4 volts. Can you feel it? I can see it changing color, so I know things are going to change soon. It's still there. 123, 5.5 volts. Heavens, it's taking a bit of punishment. This has gone up into another range where they went overload. 6 volts, 7 volts, 136. I saw a flicker. Now just note what's going to happen here. On this side our LED is dying. Bang. There we go. So there's another use. I've still got the power supply set on the settings where blue, so roughly around 9 odd volts. And as you can see, we've actually blown the circuit inside this LED, which is allowing it to pass electricity. So we still have pressure, obviously, but the circuit is now broken, so it's holding the pressure, but the volume of electricity that was flowing through there, and I forget what it was, 100 and something odd milliamp, has now stopped because the circuit is broken. Anyway, I hope that was a fun little demonstration. Ideally hope you did learn something from it. If you do have any questions or what have you, then certainly do pose them. And again, I ask my more senior and wiser viewers who watch this, if you have picked up any mistakes, then do let me know so I can annotate and make the corrections. Thanks very much for watching. As I said, please do post any answers to the quiz question and we'll cover that off in the next video. And if you think someone else might gain value from this video, then certainly please do share it on your Twitter or Facebook. It certainly helps me, and give it the thumbs up if it gave you any value at all. Thanks for watching, and we'll catch you soon.